physics 1 of being thrown up and getting thrown down. So hopefully you remembered it. You can see already that these problems are harder. They expect you to pick out the variables, where in physics 1, they basically handed you the variables. So that makes it harder. But that's the whole idea behind the harder level of physics. You're expected to know more math, and you're expected to have better reading comprehension. So, as I've said so many times, physics develops your mind perhaps better than any other subject, because it involves science, math, and reading. So no other subject, like biology, doesn't involve much math. And an English class is never going to tax your reading skills to the degree of a physics class. So it's the best thing for developing your mind, which is, I think, the main reason why the ACT scores go up so much. It's mainly physics. Okay, so let's start with 2. Jessa, what do you have for 2?
I got 4.18 meters per second, 8.83 meters per second.
Okay, so A is right, and that's going to be a negative. Now B, if you're talking about speed, if you come back to the same spot, you're talking about velocity. If you come back to the same spot, then it's 0. Your displacement is 0. So we have x final minus x initial, but x final minus x initial gives us 0 displacement. Okay. All right. 4. Does everyone understand? Okay. Lincoln, do you have 4?
For A, I have 8.889, and for B, I have 17.778.
Okay, so it was first you had to figure out the time. So the eastward run, remember we're working with our equation that the average velocity is change in x over change in time. So therefore, the change in time is going to be change in x over the average. Okay, so we have change in time over the average velocity gives us 40 seconds. And then the westward, again, the distance over this average velocity gives us 70 seconds. So we have 110 seconds. So the total distance traveled is 480. We divide by the time and we get 4.4 meters per second. Did anybody get that one? Okay, good. And now in B, we have our average distance over average time, where it's negative 80. Okay, so now we're looking at the displacement. The displacement of 200 minus 280 gives us negative 80. And so this is our average velocity versus average speed. Now those are 2 totally different things, aren't they? So if you turn around, if someone, in case Connor's up for it, I sent him the video, but if he's sick, then there's no point in him watching it. But if you can text him, if you could just text him that he has the video, for some reason he's up for watching it. Okay. 6. Naomi?
I have 2.8 meters per second, and I have 1.2 meters per second. C, I got 2.8 meters per second.
Everything A and B are right. Okay, so we have our displacement over time. We get 2.8. Displacement over time, we get 5.2. And then it's 20.8 minus 5.6 divided by a time of 2 seconds. The change in time is 2 seconds. So we get 7.6. So we're using this equation over and over again right here. Your average velocity is your change in distance over change in time, and your average speed is the distance traveled over change in time. They are the same unless something turns around. And if something turns around, they can be entirely different. Okay. 8.
Wait, I have a question. Isn't that like the distance?
What?
Like 2.8, or is that the velocity?
20.8. Oh, 2.8 meters per second. That's the velocity. Distance was 20.8. Okay, 8. Oh, we didn't do 8. 10. Tori.
For A, I got at 4, B at 1, C 4, D 2, E 4.
I think everything's right, but C should be 5. So it's 4, 1, 5, 2, and then 3. I can't remember if you got that one. So we're just looking at the slopes. Everyone can see where it's 0 for the first one. Positive 0.1 for B. Negative 5. Positive and increasing 2. Positive and decreasing 3. Did anyone get all of those? You understand? Okay. Then we had 11. Connie, did you get 11?
Oh, I thought we didn't do that. It was odd.
Thought I gave 11. Did I write it on the board? Or, yeah, it's right there. Samuel, do you have 11?
I've got to reduce one fractions, but for the first one, I have 0.5 over 2. For B, I got 1.9 over 5. For C, I got 16 over 40. For D, I got 11 over 10. Or, excuse me, 0.1 over 10. For E, I got 0.1, or negative 0.1 over 10. For F, I got 12.2 over 10. And then for G, I got 13.
Okay, so let's go through that one. So you're getting the slope. So you pick 2 points on that graph. So for A, like I can pick 20 and 40, okay? And then I can go 20 divided by 3. That gives me 6.7. Does everyone see that? If I do the change in time of 3 and the change of y of 20, I get 20 over 3, which is 6.7. Okay? The next one, B, it's the same exact line. I have to have the same slope. C, that's a horizontal line. The slope is 0. D, okay, so I'm going to pick the point from 5 to 6 seconds. That gives me a change in y of negative 40, a change in time of 1, so I get negative 40. Similarly, E is the same line, negative 40. F is basically the end of that same line, negative 40. And then G, you're again have a horizontal tangent at 0. Did anybody get all of those? Do you understand? You know how to get slopes. Does everyone understand what went wrong? Okay. We never did 12. It's even one, but we're going to do it together. Tori, could you please read 12?
Figure 2.12 shows the velocity of a solar-powered car as a function of time. The driver accelerates from a stop sign, cruises for 20 seconds at a constant speed of 60 kilometers per hour, and then brakes to come to a stop 40 seconds after leaving the stop sign. A. Compute the average acceleration during these time intervals. T equals 0 to t equals 10 seconds, t equals 30 to t equals 40, t equals 10 to t equals 30, t equals 0 to t equals 40. What is the instantaneous acceleration at t equals 20 and at t equals 35 seconds?
Okay, so we have this graph of velocity versus time, and we're looking for acceleration. How do we get acceleration from the velocity versus time graph?
Yeah, area under the curve.
What?
Is it area under the curve? Present distance.
Yeah, if you look up there, you can see I have XVA and then AVX. So what do you think it's going to be? What?
It's the
So what does that mean? How do we get acceleration from the graph? Right, slope. To go from X to V, that's a slope. V to A, that's a slope. A to V, that's the area under the curve. V to the X, that's the area under the curve. Okay. Now, what do you notice about the units?
They're kilometers.
Right. And what else? Did you say something, Naomi? Hours, and then what are they on the x-axis? Seconds. So what do we have to do?
Changing.
Right, you can either put hours into seconds or seconds into hours. Let's just put the hours, let's just make it kilometers per second. So you're going to have to convert that. Now, so first, compute the average acceleration. So these are secant lines, right? Secant lines, you have 2 points. T equals 0 to t equals 10. So you're just getting that slope. That's not hard at all. Okay, so put that hours into seconds. And then you're going to do change in y over change in x. Now notice the number of significant digits they give you. How many significant digits do they give you? 2. So your answer should have 2.
You want us to change the kilometers to miles as well?
If you want to put it in meters, you can. It didn't specify, so in that one you can do it either way. But for time, you have to have the same units. So 1 hour is 3,600 seconds. So we're getting a real small number, 0.016667 kilometers per second. Now you might want to multiply that by 1,000 and put it in meters per second so that the number's not so small, so that you're working with some more malleable number. If you do that, you're going to get 16.7 meters per second.
But how did you get 60 kilometers?
How did I get what? 60? That's on the graph. So we had to put, the only numbers we're working with are like 0 and 60. So if we put that in meters per second, we have 16.7 meters per second. Now you're going to have your answer in 2 significant digits. Okay, so now you can get it from 0 to 10. 30 to 40, 10 to 30, 0 to 40, and then you can get your acceleration. Okay, so these are all secant lines, right? You have 2 points. When they ask for instantaneous, that's the tangent line. Just getting your slopes. Changing y over changing x. Naomi, do you have a first one? I. Okay, good. So we're just dividing 16.7 by 10. Or if you did it in kilometers, you get this. Now, we can only have 2 significant digits. Does everyone follow? So we went 16.7 divided by 10, or we went, if you had it in kilometers, you would have gotten this. Okay, but we are going to put it in 2 significant digits, so we can say that's 1.7. We just write it as 1.7 because we can only have 2 significant digits, okay? So you could also write it as 1.7 times 10 to the negative 3 kilometers per second squared, either way. Everybody understand? We're just doing your change in y over change in x. Right there. 16.7. Okay, so that's your velocity. It's changing y. Now you have to divide by 10 because we're being slow. So you have to divide by the change in time. This is your change in y, that's your change in x. As you put that into meters per second or kilometers per second, you divide by 10. So it's not 60 divided by 10, it's this number right here that we call in kilometers per second.
I did that earlier. It won't say.
Okay, that's right. That's right. What's the answer to B? Lincoln, do you have it?
Um,
You actually shouldn't really have to do any work. I shouldn't say B, double I. What's the answer to double I? 30 to 40.
double I.
Yeah.
I have 5.01 meters per second.
What was your change in Y?
30.
Okay, we had to put it, actually it was 60 again, 60 kilometers per hour, but we had to put it into seconds, right? It's just the negative of A. It's the same exact thing, but it's going down. Okay, so we have negative 1.7 meters per second squared, or negative 1.7 times 10 to the minus 3 kilometers per second squared. Does everyone understand? We just went the other way, so you didn't really have to do any work. You could just see that it's going to be a negative. 1.7 meters per second squared if you have it in meters, or 1.7 times 10 to the minus 3 kilometers per second squared. So we came back the other way, and now triple I, 10 to 30. Now that's the easiest one of them all. Just so what's 10 to 30 going to be? 0. There's no change in your Y. Then 0 to 40. What's the change in Y from 0 to 40? What? 0. So what's the answer? 0. It's just 0 divided by 40, which is 0. We didn't have any change in Y. So you're just getting your slopes. There's no change in Y there. What is the instantaneous acceleration at 20 and 35? Okay, now again, you're getting the slope of that tangent line. Naomi, what's the slope at 20? Zero. The answer is 0. If you have a horizontal line, your slope is 0. You don't have to do any work. You can just see it's got to be 0. Now we want the slope at 35. Connie, can you tell me the slope at 35? We already got it. Anybody? No. Negative 1.7. We got that slope.
When did we get that one?
In the second I from 30 to 40. It's the same exact line. Okay, the slope of that line was negative 1.7. Going up was positive 1.7. Coming down was negative 1.7 and 0. Those were the only, unless they asked us to get something at like 1 or 2 seconds. Once they asked us for the secant line from 0 to 10, everything else was slopes from 10 to 40. Well, you can only have 0 or negative 1.7 on those two periods. Okay. Let's do some. So we left off yesterday. We're on 2.27. Now look at all this reading. Do you see how good this is for your reading skills? Samuel, if you can please read 2.27.
It has been suggested and not facetiously that life may have originated on Mars and been carried to Earth when a meteor hit Mars and blasted pieces of rock, perhaps retaining primitive life free of the Martian surface. Astronomers know that many Martian rocks have come to the Earth this way. For instance, searching in for ALH 84001. One objection to this idea is that microbes would have had to undergo an enormous lethal acceleration during the impact. Let us investigate how large such acceleration might be. To escape Mars, rock fragments would have to reach an escape velocity of 5.0 kilometers per second, and that would most likely happen over a distance of about 4 meters during the meteor impact. A, what could be the acceleration in meters per second energies of a rock fragment if the acceleration is constant? B, how long would this acceleration last? C, in text, scientists have found that over 40% of Bacillus bacteria after acceleration of 450,000 Gs. In light of your answer to part A, we can rule out the hypothesis that life may have been blasted from Mars to the Earth.
Okay? I want you to go through that, look it over, and write down all the variables they're giving you. Okay, remember escape speed, we talked about that. To escape the gravitational pull of Mars, they have to reach escape speed, of 5.0 kilometers per second. What would be the acceleration in meters per second squared in Gs? So first you get it in meters per second squared, and then you put it in terms of the Earth's G of 9.8. And look at your 4 equations and see which one you're going to use. Tell me one variable they give you.
Velocity.
What velocity?
The 5 kilometers per second.
Okay, so what variable is that exactly in our equations? Is that going to be initial or final velocity? Final. Over that 5 meters, it reaches that.
I thought it was 4 meters.
Oh, 4 meters is it 4? Okay, it's 4. So you're given your V final. What else are you given? You're given three variables. You're looking for acceleration, you're given three variables. You're given V final, what else? They didn't give us time.
Order didn't.
You're given V final, what else? Distance, what else? One more thing. I don't know that other thing to solve it.
Acceleration.
That's what we're solving for. What's left? There's only one variable left. We're solving for acceleration.
The initial velocity.
Right, what's the initial velocity?
0.
0. Okay, you have to figure that out to solve this problem. So you know initial velocity, you know final velocity, you know distance, and you're solving for acceleration. So look at your equations. Decide which one you're going to use. You can do it in 2 steps, or you can do it in 1 step. Why not do it in 1 step rather than 2 steps? What equations do we use to do it in 1 step? V squared. Only the V squared has one unknown of acceleration. You could have used the 4th equation, gotten your time, and then plugged it into the velocity equation. You could have done it in 2 steps. But it's much easier to do it in 1 step. So you should get used to that V squared equation, especially when you're not given time. Don't forget to put your velocity into meters per second. Because we asked for the answer, they gave us 4 meters and 5 kilometers per second, right? You can't mix those units. Show me if you have your answer. So it's just 5,000. All you had to do was change kilometers to meters. So your V final is 5,000 meters per second. get it, Lincoln?
Oh,
You can only have how many significant digits in your answer? How many significant digits can we have in the answer?
1, 3.
2. 5.0 and 4.0. Now I put 5,000 there, but technically that should be 5.0 times 10 to the third. I put the digits in the end. Connie, what did you get in scientific notation?
1 times 10 to the 6th.
Good. It should be 3.1 times 10 to the 6 meters per second squared. Now they ask you to put this in terms of G. So what do we do to put it in terms of G? All it was 5,000 squared divided by 8. How do we put it in terms of G?
Divided by 1.8.
Right. And then answer the question. Write down whether it rules out the hypothesis or not. What do we get in terms of G?
3.1 to the 10 times 10 to the 5th. G.
Okay, good. I have 3.2. But anyway, times 10 to the 5th G. So what's the answer to C? Does it rule out that hypothesis?
Yeah, because that's not really a small number. 400,000.
So it says scientists have found that over 40% of Bacillus subtilis bacteria survived after an acceleration of 450,000 G.
So would it be a possibility that it's less than
Yes, it's less than that. Okay. So the answer is yes. I showed a different way you could have done it. You could have used the velocity equation, gotten the time. Okay, let's go to 29. Lincoln, can you please read 29?
At launch, a rocket ship weighs 4.5 million pounds. When it is launched from rest, it takes 8 seconds to reach 161 kilometers per hour. At the end of the first minute, its speed is 1,610 kilometers per hour. A. What is the average acceleration in meters per second of the rocket? I. During the first 8 seconds, and double I, between 8 seconds and the end of the first minute. B. Assuming the acceleration is constant during each time interval, but not necessarily the same in both intervals, what distance does the rocket travel by during the first 8 seconds during the interval from 8 seconds to 1 minute?
Okay, so see what you can do. Write down what they give you. Now make sure your units match up. He asks you for the average acceleration in meters per second squared, so you have to put everything into meters and seconds. Once you get everything into meters and in seconds, it shouldn't seem that hard. So, kilometers per hour, it needs to be in meters per second. Okay, so what did you get for meters per second? Tori, for 161 kilometers per hour, what did you get for meters per second?
I got 1.0 times 10 to the 9th.
So, that's not quite right. So, did you put this into meters per second first?
Yeah.
What did you get? Is that what you got when you put it in meters per second?
Oh, I got 579,600,000 meters per second.
So we're multiplying by 1,000 and dividing by 3,600. Comes out to 44.72 meters per second. So
Do we have to divide that by 8?
what is the average acceleration of the rocket during the first 8 seconds? You have your equation right there for average acceleration, your change in velocity over change in time. What was the initial velocity?
0.
0. So you have 44.72 is your change in velocity over your change in time. Samuel, did you get it?
I got 5.59.
Good. It's the same idea in the second part. So again, in the second part, you're just doing your change in velocity over change in time. At the end of the first 1 minute, its speed is 1,610 kilometers per hour. Now, you shouldn't have to do any work in converting that to meters per second. You should know just how to put that in meters per second. How do you put that into meters per second? You shouldn't have had to do any work. What do we do from what we got previously? If we got 44.72 for 161, what are we going to get for 1,610? Right, you're just going to multiply it by 10 for 7.2 meters per second is our new one. That's not the answer to the second one. That's just converting that. 1,610. Now you have to get your change in velocity and change in time. You have to do your change Changing velocity over changing time. So we're doing changing velocity over changing time.
I'm just this directly time trying to just subtract the times.
So you're gonna have two different times, each situation. So we're doing our change in velocity over change in time. So this is our final velocity. So minus our initial velocity, which is 44.72, over the change in time, which was 60 seconds minus 8 seconds. And in B, write down everything you need and decide which of those four equations you're going to use. Lincoln, did you get the double I?
7.74.
Good. So then look at your situation in B. What distance? So we're looking for distance. They give you the time. We know our velocities, we know our times, we're looking for distance. If they give you time, are you using the v-squared equation? No, it doesn't have time in that equation. You have to pick a different equation. What equation should we use, Samuel?
Yeah.
The what?
Part one.
There's only four equations, right? Which one did you say?
The distance one. X equals
Like of 1 through 4, which one?
2.
You could do that. You can use 2 or you can use 4. I thought you said the fifth one. Maybe you said the second one.
Yes, it's
Okay, I was like, where's the fifth one? So we know our time is 8 seconds. We know our V0, that first part is 0. We know our V final, which they call Vx, is 44.72. You're solving for your distance. It's not hard. Now, if you had gotten your acceleration wrong, you'd be better off using the fourth equation, because you wouldn't need acceleration. But if you got it right, you can use that. And then you're doing the double I. To check if you have it. And the first one started out with 0 and 44. This is the second one.
Okay, makes sense.
The first one you should have about 179. Similarly, for the second one, we have our initial velocity is 44.72. We have a time of 52 seconds. That's 1/2 7.745 squared. You could have also gone delta x is equal to, using the fourth equation, we're just plugging it into our distance equation. Tori, did you get the double I yet? We have 3 significant digits. Lincoln, did you get the double I?
10,464.48 meters.
All right. Did you do this?
Oh, my original. 33,771.9.
So which equation did you use?
I used the same equation. I just added 447.2 times 52 first. 15.
Should be 44.72 times 52 plus 1/2 7.74 times 52 squared. Your initial velocity is 44.72. Your final is 447.2. You should get 1.28 times 10 to the 4 with 3 significant digits. Okay? All right, let's do another one. We're going to do 31. Now, if you just look at 31, there's only one of 2 things, and perhaps both, that you're going to be doing. Looking at that shape, tell me, what do you think you're going to be doing? There's only one of 2 things. What? In 31, just looking at that graph. Area under the curve, and what else? Slope. If they ask you to get displacement, is that area under the curve or slope? Area under the curve. And if they ask you, what variable do they ask you for if you have to get the slope? The slope of the velocity versus time graph is what variable? It's right up there on the board. What? Acceleration. Okay.
Was it 31?
Yeah, we're on 31. Who hasn't read? I think, Connie, you haven't read, right? please read 31.
The graph in figure D2.31 shows the velocity of a motorcycle police officer plotted as a function of time. Find the instantaneous acceleration at t equals 3 seconds, t equals 7 seconds, and time equals 11 seconds. B. How far did the officer go in the first 5 seconds? The first 9 seconds, the first 13 seconds.
It's not a hard question. That's a physics 1 question. See if we can get that.
Good morning.
Yes.
Is acceleration just velocity divided by g squared?
No. Your average acceleration is your change in velocity over your change in time. For uniform acceleration, we use only our uniform acceleration equations. But in this, you don't need any equations for these questions. You're just using what I just told you. You're using that graph. You don't need any equations. You don't need uniform acceleration equations. So what are you doing to get the acceleration at 3, 7, and 11? What are you getting? Anybody?
3, I got 13.3.
No, what do you do to get those answers?
I use this to initial velocity time plus acceleration.
Okay, so it's all right to do that. I wanted you to just use the graph, though, what I just mentioned. How do we get acceleration from a velocity versus time graph? Right, you just get the slope. It's a lot easier. Find the instantaneous acceleration. What's the slope at 3 seconds? That one's simple, right? What?
0.
Right, 0. Whenever you have that horizontal line, your slope is 0. Pick any 2 points on that line at 7 and any 2 points on that line at 11. And do the next part. Connie, did you get the slope at 7?
I got 2.
Okay, so I have 6.3. We have the change in y. So if I pick 2 points on that line, I'm picking like the high point and then the low point. So 45 minus 20, and then the change in time is 9 minus 5. It's sort of approximate, but so it's approximately 6.3 meters per second squared. Okay, that's my change in y over my change in x. You could have picked any 2 points on that line. You should have gotten about the same thing. Lincoln, did you get the next slope? Okay. Jess, so what's the next slope? Okay, good. Anything in the range, it's technically exactly negative 11.2, but it is a little bit hard to see there. So I have a change in y of 45. If I pick those 2 endpoints and a change in x of 4, I get negative 11.2. Now, what are you doing to get the displacement? Jessa, what are you doing for B? I just said it earlier. Right, area under the curve. So that's not hard. You start out, you only have a rectangle. Then you have a trapezoid or rectangle and triangle. Five seconds, it's easy to get that area. Naomi, what's the area of that curve? What's the area under the curve between 0 and 5 seconds? 100 is just a rectangle. 5 times 20, you get 100. Okay, now they ask you at 9 seconds. So you have to get the area under the curve from 5 to 9, and then add what you got from 0 to 5.
distance that you want to cover from your car. Why is it the displacement that I would occur? Basically, when integrating, it's called integrating. We do this a lot. So when you do more derivatives, you'll understand better. But basically, if you think of it as meters per second, times seconds gives you meters. So get back to meters. We'll talk about it more in the future, but it's called an antiderivative or integration. You take the derivative, right, you're dividing by time, that's slope. Antiderivative, you're going the other way, that's area to the curve.
We'll talk about it more in calculus more. Samuel, did you get the area from 5 to 9?
I got that. I got the area to be 270.
Yeah, it's too much.
I didn't get it from 5 to 9. I just got 9. It's what I did.
It's still too much.
150.
No, it's too much.
Just the area of the
Yeah, just from 5 to 9. Then we're going to add 100.
50. And then I added
130.
130. Okay. So it all together comes out to 230. It's like this. This is 100. This is a rectangle. It's 4 by 20. This is a triangle, 1/2, 4 times 25. So we add 100 plus 100. And then this is basically 2 times 25, 80 rather. So 100 plus 80. We get 230. Okay. It's 100 plus 80 plus 50. We get 230. And you're doing the last one. Now you're just going to 13. So you have to add the area from 9 to 13. It's a triangle. We're finishing 31. You're getting the area from 9 to 13. And then you add that to the 230. Lincoln, did you get it?
350.
No, it's too much.
All together.
Yeah, no, it's too much. So you have one triangle. Okay, so I'm showing you could have done a trapezoid. If you remember your equations for trapezoid, 1/2 base 1 plus base 2 times the height, you could have done this last one in one step as one trapezoid. For the next one, we have a triangle. It's 1/2 4 times 45. So we get 320. Okay, so we add in 1/2 4 times 45 to what we already had, and we get 320. Okay, so for your homework, these problems just go on and on, don't they? If that's good for your reading skills and your science skills, believe me, the ACT will seem a whole lot easier after this. Okay, so first we're doing 20 through, we left off on 22 rather. No, wait, we left off on 26. So 28 through 34. even. And let me give you one more. You should really try to read that chapter. So 28 to 34, 28, 30, 32, 34. And then how about we'll go from the additional problems. We'll do two, if you continue in the next section, there's additional problems. How about a 3-dot problem? You can do it. We'll give you 260. And 261. So you just have 6 problems. So 60 and 61. So if I write it out exactly, 28, 30, 32, 34, 6 problems. Okay. Now you really should be reading that chapter, especially it helps your reading skills, as I've said so many times. It helps your understanding so much. Okay, that's it.